Okay, this video is about the natural exponential function and how it applies to real life. Definitions. The natural base is the most convenient choice for a base for an exponent. This is one of those numbers that we accept in math. It has meaning, more than you want to know, like pi or I or all these numbers that we are learning. E is one of them, okay? E is what we consider the natural base for exponential functions. It is on your calculator. It's a preloaded number. You can see that it's irrational. It does not repeat itself. So there's no way you want to memorize this. You're going to use the E button on your calculator quite a bit. So using the second and divide sign, you can pull up the E in your screen. And we'll review this in class when you have the calculator in front of you. So the natural exponential function looks like this, e to the x power. All right, and you can generate e to the x power using the keystroke of second and the ln, which we'll do this in class. But this is the function, f of x equals e to the x power. Now if you put that in the y equals in your calculator and you graph it, look at this. It looks like the parent exponential function, and it is. That's pretty much what's going on there. So just keep that in mind as we move along. Now, finding the natural exponential function, using your calculator, we're going to round to 3 decimal places like we said before. So you're simply going to type this in, e to the -2 power, and rounding to 3 decimal places, you just get 0.135. On number 2, typing it in, e, that's telling me that x is -1, so e to the -1 power is going to give me 0.368. And I'll show you on a calculator how to get those two. The next part is to graph natural exponential functions. Okay, there's your e. Notice there's things happening to my x. There's a coefficient out here. What's going to happen here? Well, what you're going to do is you're going to type this equation in the y equals on your calculator, and you're going to look at the table. Okay, remember how to find the table is second and graph, and it's going to pull up the table. And I want you to look at the values from -2 to +2, just going both sides of that y-axis. So notice what's happening here. My y values are not getting any bigger than 3, really than 3. So 1, 2, 3. I'm just going to keep it simple. All right, and I round it to 3 decimal places. Now notice something right here. Where x is 0, y is 2. Well, let's think about this. That would be 0 times 0.24, which would be 2 times e to the 0. Well, anything, again, to the 0 power is a 1, right? So that's why at 0, my y value is a 2. All right, now let's plot some points. At -2, it's just a little over 1. -1, it's about a little over halfway. At 1, it's about 2.5. And at 2, it's a little over 3. So I'm getting my curve showing very clearly where it hits that y-axis. This point where it hits the y-axis is your most important point, and you want to make sure that's very clear on your graphs. So make sure you show your tables, which you can generate through your calculator, but make sure you graph cleanly, neatly, and that point where it crosses that y-axis is very clear. All right, let's try another one. Same process again. We type this into the y equals. Look at my table first, all right? X values from -2 to +2. And then look at my y values. The highest the y value is even going to get is a 0.562. So here's 1. Let's just name this 1. This is 0.5. Nothing's going to be 0, right? I'm sorry, nothing's negative. Again, look at where x is 0. What's happening? Well, this becomes -0.058 times 0 is 0. So 1/2 times e to the 0 power is the same as 1/2 times 1, so it's 0.5. That's why when x is 0, y is 0.5. And then I'm going to place my points just around it. Okay, so at -2, it is at 0.562, so just a little bit above that. 0.53, 0.5, 0.72, and 0.44. So notice what's happening here. This negative right here is reflecting it over that y-axis, so it's just a little bit of a curve there. But I'm making this very clear that this is at 0.5. Okay, how do you apply E to real life? Well, there's some very significant real life applications. One is with compound interest in banking. If you ever plan to invest, this will interest you. Okay, generally here it goes. It says after T number of years, the balance, which is referred to as A, in an account with the principal P and an annual interest rate of R, which will be put in decimal form, is given by the following. Okay, it just depends on how it's compounded. For n compoundings, like it tells you how many times it will compound during the year, then you're going to use this first equation. All right, just this first equation. So the principal times 1 plus the rate divided by the amount of compoundings raised to the number of compoundings times time. Complex formula, you need to know how to use it. Okay, this is for n number of compoundings. Now, if it's a continuously compounding account, which is really what you would want, you would use this equation. And notice that there is an e involved. That's why we're bringing this up. This is a very commonly used equation in banking and finances. So A equals the principal times e raised to the rate times the time. Okay, those are my equations I'm going to be using in these application problems. So here's an example. A total of $12,000 is invested at an annual interest rate of 9%. Find the balance after 5 years if it is compounded, first of all, quarterly, and then continuously. So I rewrote these equations for you, but let's identify some things first. Okay, $12,000 is going to be my principal. Okay, that's the P. That's how much you put in the account to start it. The rate is 9%, but as a decimal, you have to put it as 0.09. The time, 5 years. Okay, those are the 3 things I need to identify before I can plug into my equations. So I want to know the account balance, and it's $12,000. 1 plus the rate, 0.09, over, okay, n, well, that's how often is it quarterly? Well, if it's quarterly, how many times a year is that? Think about how many quarters are in a dollar. That makes n equal to 4. If it was monthly, it would be 12. If it was daily, it would be 365. Weekly, 52 weeks in a year. So think about those things you already know. Quarterly would make it the n equal 4. So it's 0.09 divided by 4, raised to the 4 times t. T is 5. So that's a lot of complex computations. And you're going to want to put this in your calculator very carefully. And I'll show you how I'm going to do that. Okay, so part A, when I type this in, I want to be very careful. I'm going to say 12,000 plus, 12,000 times 1 plus, and I'm going to use alpha y equals to give me a fraction. Remember, my numerator is the percent as a decimal. Denominator is my compounded quarterly, so that's a 4. Come out here, close my parenthesis, raise it to the power of 4 times 5, which I can multiply that, that's 20. And then I hit enter. And there's my solution. Now that I've done that, I get that the account balance then is $18,726.11. Since it's money, we round to 2 decimals. That's what we do. Part B, let's do this continuously compounded one. What happens? Okay, if my account balance then will be my principal times e raised to the 0.09 power times 5, which is my time. Again, be careful how you put this in your calculator. And let's look at that. Problem. For the compounded continuously, I would do 12,000. Oops. Times e, second, ln, raised to the, this side use parentheses here, 0.09 times 5. And then I'm done with that. Enter. And there's my amount of money, account balance. So my account balance, having done all that, comes out to $18,819.75. So which is better? To be compounded continuously, you're going to make more money than if it is quarterly. Doesn't look significant, but over more than 5 years, it will become more significant. All right, so another application of exponential is with E is exponential growth or exponential decay, which is given in this example. Okay, it says let Q represent the mass of radium, whose half-life is 1,620 years. The quantity of radium present after T number of years is given by this equation. So you notice that T is in the exponent. That's why we're bringing this up. Okay, so multiple things we need to do here. First of all, we're going to sketch a graph of the function over the interval from t equals 0. So we're going to make time our x-axis and our quantity our y-axis. And we're talking in grams here. Okay. So our time, it says, has to start at 0, which is 0, 0, and go to 5,000. So this is 5,000 years. Determine the initial quantity when t is equal to 0. Well, let's look at this equation. What happens if we put in a 0 over 1620? That's the same as 0, isn't it? What's anything to the 0 power? Anything to the 0 power is always a 1. So this is really 16 times 1, which means it's 16 grams. So at 0 time, it's at 16 grams. All right? So determine the initial quantity. So for part B, I would say it is 16 grams. A is obviously my graph. C. Now to finish our graph, what's going to happen to it as time progresses? If you're not sure, take your calculator, plug this into your y equals, and you're going to see that this is exponential decay. So what's going to happen is it's going to do this thing, okay? And what I need to do for part C is figure out what would it be at 1,000 years? What's that quantity right there? How many grams is that? So I would type it into my calculator. I would say 16 times 1/2 raised, this is where you'd use another set of parentheses, of 1,000 over 1620. Let the calculator do the thinking for you. Let me show you. For the last example, as I type this in, I'm going to do 16 times 0.5, which is 1/2, raised to the alpha y equals 1,000 over 1620. And I'm going to close that parenthesis. And there's how many grams it was at 1,000 years. When I get that, I get 10.43 grams. I would say the quantity after 1,000 years is approximately 10.43 grams. All right, so A would be my graph, B would be my answer here, and C, what I plugged into my equation. Okay? All right, for the whisk, you're going to do this one. This is back to interest. Notice it's compounded continuously, so you're going to use this equation. Plug in your values, consider interest rate, and how you should write that in there. Try to do this in your calculator. If not, you can do this in class first thing, and then we can come up with an answer together. But I at least want you to set up the equation for me. Okay? Good luck, and see you in class.